Dear students, today we are going to discuss about stereoisomerism. So you have learned isomerism in your HS level. In there you have found chain isomerism, position or group isomerism, and then functional group isomerism. Now here stereoisomerism, it is an isomerism is discussed in the structures which are three-dimensional in nature. Now, although we write our carbon and the other four different groups in this way in normal structures like this, but actually it is not true. The carbon structure is like this. A carbon is having four different groups. It has this type of structure. That means it is a tetrahedral structure and it is a three-dimensional structure. Now, these three-dimensional structures can have different isomers, and this isomerism is called stereoisomerism. Now, before going into the detail of stereoisomerism, we have to study a little bit about the different type of representation of structures. Now, that is called projection of structures. Now, one structure can be projected in different ways. What are those ways? Number one is Fisher projection. Now, in this Fisher projection, we generally used to write down the structures in a form like this. That means it is having a 90-degree angle in between the bonds. Suppose here one carbon is there, other hydrogens are here. So this is simply the Fisher projection where the bonds are represented as 90-degree angle. Now this Fisher projection structure we can also write in bigger structures like this. Suppose this is a diol which can be represented like this. This is called Fisher projection formula. Next one is Newman projection formula. Newman projection formula. In this formula, if we have two carbons, then we can write down the structure in this way. Suppose if I write down the first carbon where three other groups are there, suppose these three are hydrogens, and the second carbon is written like a circle. So this circle is having another three hydrogens, suppose like this. So this back side means another carbon is there, front side means one carbon is there. That structure is like this. Suppose this structure, you can see this is the front carbon where three other groups are there. This is the back carbon where three other groups are there. So this representation is known as Newman projection formula. Now what we can do, we can rotate this carbon by keeping fixed this carbon, second carbon. That means we can rotate this one and by fixing this one. So during this rotation we will get different conformations, and those are different Newman projection structures. Suppose like this, we can have also this structure when like this, these hydrogens are just above this hydrogen. So then it will be called as eclipsed structure. So this one is eclipsed. Suppose this red ball is just above this blue ball, so you cannot see the blue ball if you observe only the red ball. So this structure is called eclipse. Similarly, this one is eclipsed with this one, and this one is eclipsed with this one. Next structure is Newman projection. After this Newman projection, we can have Sohor's projection structure. Now in this Sohor's projection structure, what we used to do, we have the same molecule, but we will write down the structure like it is like a jumping horse. Suppose this is the head of the horse, this is the tail of the horse, these two are the front legs, these two are the back legs. So we will just write down the structure like this, and then it can represent the Sohor's structure. This is called Sohor's. Again, we can do the same thing. Suppose keeping one carbon fixed, another carbon we can rotate. So the structure will be looking like this. Suppose if we have rotated the structure, then it will look like this. This is called Sohor's projection structure. Next one is called flying wedge structure. Flying wedge. In this case, we have to learn three types of bond representation. This bond is called on the plane. That means I am writing on this board. Here this bond is present. This bond is above the plane, and this bond is representing below the plane. So these three are the types of bonds that is used in flying wedge projection. Actually, this flying wedge projection is the three-dimensional representation of the structure. Now we will write one carbon like this. Suppose if we have one carbon, in this carbon these two bonds are on the plane. This bond is above the plane, this bond is below the plane. So we can have different groups, and this is the three-dimensional representation of this flying wedge structure. Similarly, we can have two carbons also. If we have two carbons, these bonds are on the plane. This bond is above the plane, this bond is below the plane. In this way, we can represent the Fisher projection formula. Flying wedge formula. Another that is not very much important, but still we have to learn this. If we have to learn write a big molecule, in organic chemistry we did so many big molecules. So big molecules we used to write down like this. This is called zigzag structure. So in this zigzag structure, each point is representing one carbon, and here we can give some groups like this. So this will represent different groups present there, and also the carbons which, if no other group is present, that means there are two hydrogens. So all these points are CH2, and here this one hydrogen is replaced by OH. So these are the main projection of structures that we can find in organic chemistry. So after this, we will learn how to change one structure to another structure. So suppose if we have a Fisher structure, Fisher 2 so horse, how we can represent this one? Suppose if we write down the Fisher structure like this, suppose this is OH, this is OH, CH3, hydrogen and hydrogen. Then first we have to draw the middle bond, this middle portion, and then we have to add the OH and the hydrogens like this, as it is present here, OH and hydrogen, and the two groups, these two vertical groups will be below like this. This is the direct conversion from Fisher to Sauer's. So thank you.